Welcome to the Greek Ship Corrosion channel. I'm Ehtesham Zade, a researcher in the field of corrosion and protection of materials. More information about this channel is available on video number E28. Chapter 4, Section 3, Electrode Kinetics and Kinetics of Corrosion. Tafel Equation, Activation Polarization, Concentration Polarization are the topics of this video. Polarization describes the shift in an electrode's potential away from its equilibrium state induced by the flow of current. Polarization causes the anode's potential to become more positive, novel, and the cathode become more negative, active, relative to their reversible potentials. Anode, cathode. Who is Tafel? Julius Tafel is known for Tafel Equation. He worked first with Hermann Emil Fischer on the field of organic chemistry, but changed to electrochemistry after his work with Wilhelm Oswald. The Tafel equation is an equation in electrochemical kinetics relating the rate of an electrochemical reaction to the over potential. The Tafel equation was first deduced experimentally and was later shown to have a theoretical justification. The equation is named after Swiss chemist Julius Tafel. Polarization equals positive negative beta times logarithm of current density over exchange current density. Eta A activation polarization in volts, beta Tafel slope in volt or volt per decade, I current density in amperes per square meters, I0 exchange current density in amperes per square meters, is derived from the Butler-Volmer equation under conditions where either the anodic or cathodic reaction is dominant, allowing for simplification. Tafel equation helps determine kinetic parameters such as exchange current density and the Tafel slope, providing insights into reaction mechanisms and electrode behavior. It's widely used in corrosion studies, battery science, and fuel cell research to understand and optimize electrochemical processes. Butler-Volmer equation. The Tafel equation is an approximation of the Butler-Volmer equation in the case of the absolute value of eta is greater than 1/10 volts. In electrochemistry, the Butler-Volmer equation is one of the most fundamental relationships in electrochemical kinetics. An example is shown in this figure. The horizontal axis is potential, and the vertical axis is current density. The total current density equals anodic current density plus cathodic current density. The red curve is anodic current density and the blue curve is cathodic current density. It describes how the electrical current through an electrode depends on the voltage difference between the electrode and the bulk electrolyte for a simple unimolecular redox reaction, considering that both a cathodic and an anodic reaction occur on the same electrode. Activation polarization. Activation polarization refers to electrochemical reactions that are controlled by a slow step in the reaction sequence. Please watch video number E22, Chapter 4, Section 1. Overvoltage is the excess potential required for the discharge of an ion at an electrode over and above the equilibrium potential of the electrode. In this figure, oxidation and reduction reactions corresponding to a hydrogen electrode are plotted with beta value of 1/10 volts. the reaction rate changes by 1 order of magnitude for each 100 millivolts or 1/10 volt change in overvoltage. 100 millivolts, 1 order of magnitude. Anodic branch, cathodic branch. The relationship between overvoltage or potential and the logarithm of current density is a linear function. The value of beta for electrochemical reactions ranges between 0.05 and 0.15 volts. In general, beta is usually 0.1 volts. Concentration polarization. Concentration polarization refers to electrochemical reactions that are controlled by diffusion in the electrolyte. This is illustrated in this figure for the case of hydrogen evolution. Please watch video number E22, chapter 4, section 1. This arrow shows the direction of diffusion of H+ ions toward the surface of the metal. The hydrogen evolution reaction involves the reduction of hydrogen ions at an electrode surface. At low reduction rates, the concentration of hydrogen ions near the electrode decreases. As the rate increases, the reaction becomes limited by the diffusion of hydrogen ions to the electrode surface, reaching a limiting diffusion current density, IL. Low reduction rate, high reduction rate. Limiting current density represents the maximum rate the reaction can proceed, dictated by how quickly hydrogen ions can be supplied to the electrode. Understanding this is crucial for optimizing electrochemical processes. Limiting diffusion current density equation. IL is expressed by the equation IL equals D times N times F times CB over X. IL, the limiting diffusion current density. D, the diffusion coefficient of the reacting ions. CB, the concentration of the reacting ions in the bulk solution. X, the thickness of the diffusion layer. Some consideration about limiting current density are shown here. A. The provided equation describes the limiting diffusion current density in an electrochemical system. B. This current density is directly proportional to the diffusion coefficient D and the bulk concentration CB of the reacting ions, and inversely proportional to the diffusion layer thickness X. C. A higher diffusion coefficient or bulk concentration leads to a higher limiting current, while a thicker diffusion layer reduces it. D. This equation is fundamental in understanding and quantifying mass transport limitations in electrochemical processes, such as in polarography or voltammetry. E. X is influenced by the shape of the particular electrode, the geometry of the system, and by agitation or turbulence that decreases the thickness of the diffusion layer because of convection currents and consequently increases the limiting diffusion current density. F. Calculation of X is extremely difficult except for very simple systems. G. X must be determined by empirical experimental measurements. H. It should be noted that many useful qualitative predictions and correlations can be achieved merely by the knowledge of the relationship between IL and other factors of the particular system. Variables affecting limiting current density. This figure demonstrates how the shape of a polarization curve observed during concentration polarization is influenced by variations in the limiting diffusion current density. Increasing velocity, increasing temperature, increasing concentration, increase limiting current density. Changes in this density directly impact the mass transport processes near the electrode surface, altering the curve's characteristics. As the solution velocity, concentration, or temperature increase, limiting diffusion current density increases, since all of these factors exert an influence, as indicated here. Concentration polarization equation. If there is no activation polarization, then the equation for concentration polarization in an electrode is eta C equals 2.303 R times T over NF logarithm of 1 minus current density over limiting current density. Concentration polarization doesn't become apparent until the net reduction current density approaches the IL, in which over voltage is equal to infinity. Both activation and concentration polarization usually occur at an electrode. At low reaction rates, activation polarization usually controls, whereas at higher reaction rates, concentration polarization becomes controlling. So, the total polarization of an electrode is the sum of the contributions of activation polarization and concentration polarization. The equation for the kinetics of anodic dissolution is given by eta of dissolution equals beta logarithm of current density over exchange current density, anodic branch. And the equation for the kinetics of reduction reaction is given by eta of reduction equals minus beta logarithm of current density over exchange current density plus 2.303 RT over NF logarithm of 1 minus current density over limiting current density. Cathodic branch. Here, anodic branch shows only activation polarization, and cathodic branch shows activation polarization and concentration polarization. Challenge number 57. Thank you for your time and attention. If you like to challenge yourself, please answer this question in the comments section. Limiting diffusion current density IL is usually only significant during the reduction reactions, cathodic branch of polarization, and is usually negligible during the metal dissolution reaction or anodic branch of polarization. Why?